Good afternoon, folks. My name is Jeremy McGovern, and this is our Shear Analysis Report. Here at Metal Industries, we understand the importance of airfoil design. That is why we are offering our services to provide experimental shear center analysis on wing sections. With our technology and our experience, we are confident that we can show you how reliable our services are and how accurate our results are by comparing it to our theoretical calculations. Wing twisting plays a vital role in the structural mechanics of an airplane wing. This form of deformation causes premature failure in the structure that otherwise wouldn't have occurred. Understanding where to concentrate shear on an airfoil can completely cancel the resulting twist of the load. The shear center of a body is defined as a point about which the external load has to be applied, so that it produces no twisting moment. It is clear that the determination of the shear center would yield worthwhile results. The objective of this experiment was to experimentally locate the shear center of L and C beams. This was done by applying a constant force on the cross-section of the beam and measuring the beam's deflection on its ends. The results were then compared analytically to Euler-Bernoulli model for verification.
Hello everyone, my name is Chen Wang. Here's how we predict the shear center location. For the CB, we can assume that the shear center location will be outside of the bar, because we know that the net moment acting on the shear center location will be equal to 0. So it will be located as somewhere on the x-axis, because this is a symmetric shape. For same reason, we assume that the shear center location of the L beam will be located at the cross section. This is a general equation for the shear flow. We need apply the shear flow to calculate the shear center location. Because we did the C beam and L beam is symmetric, so the second moment inertia Ixy will be equal to 0. So the equation will be simplified to here, this equation. So we can see that we know that the force the moment created by the bottom bar and top bar will be cancelled by the moment created by the vertical bar. So we can get an equation, this one, to determine the location of the shear center. C will be the location of the distance from the vertical bar to the shear center location. Here is a simplification equation of the C. Lab will only output voltage, so we can use the voltage times the calibration factor to get the displacement for our experiment.
My name is Jay Patel. After we found calibration factor, the next step will be measuring the dimensions of the cross-section beam. Those cross-section dimensions will be used to obtain theoretical values of shear center. We used vernier caliper to measure the cross-section dimension of the beam. And right here you can see these are the dimensions we found for the cross-section. Talk about how we use this experimental apparatus and why we use this. So first, why did we use this? Because this apparatus will allow us to generate twist in the beam, and it will generate twist by applying the load at the weight hanger, as we can see on the side view. The load in this experiment will be stay constant. We use 8 pounds for this experiment. As you can see, once we attach the loads here, it will start pulling it down, and on the top view there, it will apply the loads on the notches. And once we apply the load, we use two linear potentiometers to record the displacement. So in this slide, we have a close look of the top view and a picture of notch bar. In the closed look, as you can see, we have a two linear potentiometer fixed with the mount, and we have a rotating disc, so we can move this apparatus in 0 degrees and 90 degrees for various load, various applying load locations. The notch bar is attached to the top, attached to the free end of the cantilever beam, so we can apply load on various locations of the cross section of the beam.
My name is Eduard, and today I would like to talk to you about the results of our experiment. First off, I'll be talking about calibrating our linear potentiometers. The potentiometers measure a voltage, but the measurement we desired was beam deflection. Therefore, both the potentiometers were calibrated at the beginning of the experiment by applying known deflections to the sensor collecting data for the corresponding voltage. As you can see from the figure on the screen, we've graphed deflection versus voltage and used a trend line between points to find the relation from the equation of the curve. You can see from this graph that it was necessary to calibrate both linear potentiometers, since one was found to be much more sensitive than the other, with a slope value of -1.33 and another one of -0.99. In summary, shear center is the location at which the cross-section will not have a moment. That is why in this experiment, we tested the deflection on both sides of each cross-section at a variety of different locations. Now these are experimental results for the C cross-section beam. In these figures, the twist of the beam is plotted as a function of load location on the cross-section. The y-axis values is the displacement from our linear potentiometers, and the x-axis values is the location at where the applied load was. As you can see, the potentiometer on the left side of the cross-section is shown in orange, and the potentiometer on the right side of the cross-section is in blue. The resulting intersection of the graphs gives the coordinate position of the shear center. As you can see, the one on the left does not clearly show the intersection. This is due to solely changing the position of the applied load towards the left potentiometer. So instead of applying a load at every notch, we only applied it at the left half of the beam cross-section and used the trend line equations to determine where the shear center was located. For the C-beam, it was experimentally determined that the shear center was -0.47 and 9.29. These are the L-beam deflection graphs for both orientations. For the L-beam, it was experimentally determined that the shear center was -2.04 and 9.54. Now, although these coordinates do not match with our predicted shear center location, it's important to note that this was caused by a variety of errors and restrictions. Such restrictions include not being able to adjust the load angle due to the structure of the apparatus, as well as short and faulty wires on the linear potentiometers. Although the data is correct, the use of better equipment would help in finding shear center with respect to the desired axes.
My name is Mike Allen, and overall we feel confident in our abilities to be able to determine the location of the shear center for the C and L beams, and our ability to apply this to gain knowledge to future experiments in other cross-sectional shapes. A source of error in our experiment included the string and pulley that held the weights. It was crucial to ensure that the weight in the pulley was perfectly aligned with the marking on the apparatus to ensure that the load was applied in a purely axial direction. Due to human error, we believe that our load had some other directional component to it. There was another error was loading and unloading the apparatus. We had to make sure that the weight was not applied too quickly to prevent damage to the apparatus. Another source of error was, since the beam was previously tested from other groups, there could have been micro fractures, fatigue, and defects within the beam, which could impact the results of our experiment and the shear center location. The sample was in a cantilever configuration within the apparatus, but may have not been perfectly cantilevered due to the sample having to be bolted in by hand. For more accurate results, this experiment could have been repeated, and the load position when moved could have been taken in both directions with respect to the starting point on the pulley instead of just one direction. We're confident with proper funds, better equipment, and considerations that the errors we faced in this experiment could be avoided. Thank you.